On the next few slides, we're going to talk about something called a linear combination. So first, let's look at the definition. A linear combination of a set of vectors. So here we have a set of vectors v1 to vp. These vectors are in Rn. That means that they contain n elements. And we have scalars c1 to cp. To make a linear combination of this set of vectors, what we do is take these scalars are just constants, and we multiply it by each of the corresponding vectors, and then we find the sum. And so we end up with the following. So a linear combination is any vector y that can be written in this form. Now let's look at the following question. It says, can this vector b, which is 0, 1, be written as a linear combination of the vectors v1 and v2? So if we use the definition of linear combination, we know that we write the following. B is some scalar c1 times v1 plus another scalar c2 times v2. So the question is this statement a true statement? So I've taken this statement now, can B be written as a linear combination of v1 and v2? And I've just simply inserted the corresponding vectors b, v1, and v2. Now if you remember, if we c1 and c2 are scalars, that just means that they're constants. So whenever I want to multiply a vector by a constant, I simply take the constant and multiply it by each element in the vector. So that's all I've done here. Now I've translated this in the next in the green box back to a linear system. So we have 2c1 plus c2 is equal to 0, and 3c1 plus 2c2 is equal to 1. So this also is asking the question, can B be written as a linear combination of these vectors v1 and v2? But now we have a linear system. And what we want to know is, does the linear system have a solution? If B can be written as a linear combination of v1 and v2, that's what this statement says, then that must mean that this linear system must be consistent or must have a solution. So our goal now is to determine whether or not this linear system, sorry for that little slip up. So again, the goal is to determine whether or not this linear system is consistent. It just happened again. All right, third time's the charm. So hopefully this time everything won't disappear. So we have this linear system and we want to know whether or not it is consistent. So to do that, notice that I have found the augmented matrix for the linear system, and now I'm going to put it in row echelon form to see whether or not the linear system is consistent. If it is, then B can be written as a linear combination of v1 and v2. So I invite you to pause the video now and attempt to do this on your own, and then compare your result to what I'm about to write. So hopefully when you performed your row operations, again, you may not have the same ones that I have, but hopefully you got something that looked like the result that we have here. Notice that in this matrix, there is not a pivot in the last column of the augmented matrix. We have a pivot here. Again, a pivot is our first non-zero entry in each row, and we have a pivot here. Hence, we know that the system is consistent. Again, the reason why we know it's consistent is because there is not a pivot in the last column of the augmented matrix. We can now conclude that B can indeed be written as a linear combination of the vectors v1 and v2. By the way, these three dots written together mean therefore. So whenever you see those three dots, I'm just mean therefore. Notice that to answer this question, we did not need to solve the linear system. In fact, what we did was to put this augmented matrix into row echelon form. Again, we don't need reduced row echelon form to determine whether or not the linear system is consistent. So let's take this a little bit further. Now let's ask ourselves the following. how is B written as a linear combination of V1 and V2? That means we need to find the scalars C1 and C2 from our linear system above. Right? To do that, we actually have to solve the linear system. To solve the linear system means that we need to put the augmented matrix in reduced row echelon form. So what I would like for you to do now, again, is to stop the presentation, and you want to take the augmented matrix, which is here, and put it into reduced row echelon form to find the constants C1 and C2. So I've done the last few steps for you to put the matrix into reduced row echelon form. And that is what we see here. And now I've translated that back to a linear system. Notice that in reduced row echelon form, we actually get the solution. And I'm noticing I made an error because instead of being x1 and x2, these values should be c1 and c2. Now we can rewrite the statement that we have. Here we have b equal to c1 v1 plus c2 v2. And I've just replaced again the vectors with their corresponding values. And notice that when you put c1 equal to -1 into the statement and c2 equal to 2, that indeed we get the vector b equal to 0, 1.